this seems to be a small difference, but like this difference turned out to be quite important when you are evaluating the iterations in parallel. So to explain that difference, I think it's first important to say a little bit of how you usually compute things in parallel. So let me draw a diagram of this is the discrete space, and in the y direction is the iterations, in the x direction is the index I. So usually in parallel computing, so this is a bunch of grid points because I have a discrete space, right? So I is discrete and k is also discrete. In parallel computing, I'm assigning each set of indices, spatial indices. I'm assigning each set of spatial indices to a processor, a node or a CPU. So let's say CPU 1, and just to make it simple, let's say I just have 2 CPUs. So this is CPU 2. All right. So what I do is in Jacobi, it's very easy. So CPU 2 is going to, based on what I have here, based on the initial condition, which I already know, I'm going to compute the value here by looking at my left neighbor, right neighbor. I compute the value here by looking left neighbor, right neighbor. Compute the value here by looking left and right neighbors, right? That's what I do in Jacobi. So this is, let's say this is k plus 1, this is k. I can compute all these values that CPU 2 I am responsible for. And CPU 1 does the same thing. So CPU 1 computes these values by looking at these neighbors, right? Okay, so what's next is a little bit tricky because the CPU 2 has computed the red numbers at k plus 1. But in order to advance to k plus 2, I actually, if I want to compute here, I need the information the green CPU, CPU 1, just computed. So I need to communicate. The CPU 1 needs to send the value it computed over here to CPU 2. And the CPU 2 has to send this value to CPU 1 so that CPU 1 can compute the rightmost grid point, right? So it needs to communicate. Okay, so this is easy in Gauss-Seidel. Basically, after every iteration, I'm going to send whatever information the other CPUs need to these other CPUs.